So sorry. So the last thing I'm going to be talking about this week is hydrostatic equilibrium. I'll write that out. Now, this is certainly a very dramatic and technical sounding and probably pretty intimidating term. But don't worry too much. I think conceptually, hydrostatic equilibrium is not too difficult to understand, so don't panic. I think y'all got this. So, what is hydrostatic equilibrium? Well, hydrostatic has hydro in it. It means like water. It's actually a concept that we borrowed from the physics of like how fluids and gases interact with each other and exchange heat and stuff like that. When you have the star, like the sun, just made up of a bunch of gas. Gas is not really bound to itself. It can flow, it can compress and fill a container and stuff. So we can borrow a lot of concepts from the way fluids work to describe the sun. And so, what is hydrostatic equilibrium? Well, how am I going to put this? So, the sun has a lot of gravity, right? It's very big, has a lot of gravitational power. But the sun's not that dense. It's only a little denser than water when it comes down to it. So, why doesn't the sun pull itself into a smaller, denser ball, right, with all that gravitational power? Why not make itself more dense than water, for instance, Why is that a problem? Well, the thing is, it actually comes back to what I was talking about several videos ago about the balloon that's getting heated up. I talked about how, even though I have the same amount of air inside, that its density decreases when the air heats up. The molecules get further apart, and the balloon expands to kind of accommodate that. But another way of thinking about it is, as the air molecules heat up, they're bouncing around at high speeds. They're imparting a lot of force, a lot of energy onto each other when they hit each other, but also onto the outside of the balloon. The inside, like the inside edge of the balloon, when it hits up against the walls of its container, the balloon, right? So that applies a force, a pressure, to the inside of the balloon, which causes the balloon to expand out. That's the other thing about heating up a gas. It increases the pressure of the gas. If gravity could work on the sun unopposed, right, with nothing else hindering it, nothing else involved, it would crush the sun into an extremely small mass, right? It would just keep on pulling in on all of those atoms with all of that gravitational power, and it would just never stop. So the reason it stops is because the sun, when it produces all this energy with the proton-proton chain, produces so much heat, heats up its molecules, they start to push out. They're bouncing off each other. They're moving all over the place. When they heat up, they create an internal pressure which pushes outward and opposes the gravitational pressure which is pulling inwards, right? The gravity can't pull in forever because at some point the internal pressure of the gas's energy is going to stop it. And the point, the size and temperature and stuff, the size and density and temperature, the whole state of a star, like the sun, where its internal energy pressure and its inwards gravitational pressure are balanced is hydrostatic equilibrium. The sun is the density and size that it is because for the sun's particular situation with how massive it is and how efficient it is at producing energy, that size and energy is where hydrostatic equilibrium is. It's the size and energy where its gravity and its internal energy pressure are balanced. If the sun were to suddenly magically become even more efficient at producing energy through fusion, it would no longer be in hydrostatic equilibrium, because now its internal energy pressure has just gotten stronger. The sun, in that case, would grow a little bit, but then it would stop growing because now it's reached hydrostatic equilibrium again. A new point, a little bit further out, is now where the gravity and the internal pressure are matched. So, a star may not be in hydrostatic equilibrium, but it's going to start getting there. It's going to approach hydrostatic equilibrium. So yeah, that's the situation with hydrostatic equilibrium. And I think that about covers it. I think that about covers it for this week.